Yeah, okay. So thanks, committee, and all of you for being here. My talk. First of all, I'm Marcelo from Uruguay, and my talk is about an application of JuMP and related extensions that has to do with reachability analysis. So I'm going to begin with the some context of this domain, and then I'm going to into some implementation details and perhaps something that you can learn along the way that is perhaps useful for you. So I would like to convey that JuMP and method interface have a great expressive power and allow to formulate optimization problems in control and efficiently and with a slow model overhead for the creation of a model. So our proposal today is well, given a model of a system, to exhaustively and automatically check whether the model satisfies some criterion for safety. And this is the purpose of the reachability analysis. So to give some mathematical formulation, remember that differential equations are equations where you have a derivative for some state variables and you have some function f that depends on them and perhaps on some inputs and some parameter values. And what we would like to do is to consider the set of states that are reachable at some time t, okay? So this is the set R of delta for some delta. So then you can say, this is my set at time, that set that I can reach at time delta. Then I take the union of all these sets in an interval, and this is what I call the flow pipe, like that. So this notion that I've said here also extends to hybrid systems, and hybrid systems are those in which you have the continuous ODEs, and they are shown by discrete transitions. What I'm going to explain here also applies to that more general setting. So if you want to think in the simplest case, then you have x dot equal a times x. So you take an initial set x0, and then you apply the solution, which is e to the power 8t, and then you arrive at this point. What I did here was to draw some trajectories taken randomly for the initial set, and you get those that are here. Okay. So if you say I take the convex hull of the initial set and the first image, then I get the region which is shaded. But as you can see, there are some trajectories which are outside this region. So this means that if I want to give a guarantee of all the trajectories that are in this time interval between 0 and t in continuous time, then I need to do some other operation to enlarge, or what is called bloating of this set. Okay. So there are techniques to do it. For example, you can do it like that. Okay. And then, okay. And then you are able to make algorithms that work for a fixed time horizon. And then this is a research that has been perhaps in the 10 to 15 years and has led to algorithms that scale very well with the dimension, and also that are wrapping free, meaning that you don't have error that accumulates over the computation. And as you can see here, oh, yeah, now it's better. So you can see, for instance, that I start over there and I go to these trajectories. Okay. So now these methods are implemented in some of our packages that we develop in Julia Rich. So lazy sets, which is a library that allows to work lazily with sets and operations between them, and reachability that implements some of these methods. So for instance, you were able to define some constraints that the systems should satisfy, and then you want to be able to check if this is the case. I'm showing some examples. You can find more repeatability evaluations on our packages for systems that are either continuous or hybrid. Now, what I talked so far, it's about systems of affine ODEs. Now the question is, what can you do with systems which are polynomial? So this is there are different methods that people have developed, and the method that I will continue in the rest of the talk has to do with the Hamilton-Jacobi-Bellman equation, which is an equation where I have a function phi of x of t such that the initial condition corresponds to the initial set, and solutions are associated to the reachable sets at time t. So the idea is that in the paper by these people, you can transform the solving of this equation into a hierarchy of semi-definite programs. So this is where JuMP comes into play. So essentially, I'm going to take some assumptions. So the right-hand side of fx is a polynomial, and the initial set is giving us a basic semi-algebra set. This means it's giving us inequalities or a set defined by polynomial inequalities. And we are also need to give a priori enclosing set. This means that when I am going to begin, or let's say that my reachable set is bounded in some compact set and cannot go over there. So then there is an optimization problem that we can formulate. It has this look where, well, this L phi is the operator that is 0 in the solution. That takes a partial derivatives of the flow. And then you have the constraints, okay? So the optimization variables is a scalar variable epsilon and phi of xt, which is going to be a polynomial both in the states variables x and in t. Okay, so then what one can do is to relax this problem into a hierarchy of problems where I fix the degree of the polynomials, and these polynomials are constrained to be sum of squares polynomials. We can check the details. So essentially, one would like to solve this problem, and for one knows that for an increasing value of the relaxation order k, then the solution of this problem converges to the to an under approximation of the exact reachable set, and one is also able to get an over approximation. So, okay, so this is the problem that I'm going to solve now. Okay, so you have minimization, you have these constraints, and this S0 means that S0, S1, and so on. These have to be sum of squares polynomials. Okay, so how can I model this with JuMP? So I'm going to present the modeling together as so long as I present the example. Okay, the simplest example is a van der Pol oscillator. It's two-dimensional. It's easy because it's two-dimensional, but also it has some complications because it has a limit cycle. So okay. You load some packages, you define some polynomial variables, and then you define the dynamics. I'm over there. So I defined my dynamics of my van der Pol system, and then I define the initial states, like that. And then I define constraints. So you remember that constraint for the search space was g of x greater or equal than 0. What I'm going to do here is to define a function g of two variables, and then I'm going to use some macros that are provided by the polyJuMP and some squares that allow me to easily formulate the constraints of the problem. So I define the vectors of monomials up to degree 12 for this example, and I finally give my model as using the Mosic optimizer, and I calculate the Jacobian of the flow, and then I add the variables of the model, and that's essentially taking the set. Macro set allows me to find the constraints of non-negative of G, and similarly for this other domain where I don't have the time constraint. And then that's it, because then you will give the constraints to the SOS, and then you will say that these, for example, these polynomials are in the sum of squares cone. Okay. And then you call optimize, and you have some results. So the next part, I'm going to analyze these results and compare a little bit with other things that have been done in the past. Okay, so what I did was to take from the original paper that implementing JuMP. If you don't know, JuMP is a well-known tool for control theory optimization modeling in MATLAB. And if you look at if you compare the code, well, it's also compact, let's say, with 23 lines of code, and similarly for Julia code. Okay, if you put this all together. Then what you can see over here is that the number of scalar variables. So here I'm analyzing two things. I'm analyzing the size of the model passed to JuMP, and I am analyzing the time that it takes to solve. Okay. And then, well, what you can see from this table is that essentially they are in the same order, but it is often the case that sum of squares is having like half of the variables. Is having half of the scalar variables and constraints. Okay, so that's a good point. And so then I'm going to, okay, so then what I did next was to visualize this result in two different ways. So the first way was using a package called implicit equations, that you can plot the equations, the inequalities over there, and you obtain this plot where this region in between these two is the Reachset. And finally, I also used the other package that is called interval constraint programming, which is in fact more powerful in the sense that, well, I can use multidimensional interval boxes, so no, I'm not restricted to 2 dimensions, but more interestingly, because I can calculate a rigorous inner and outer approximations of these polynomial inequalities. So, for instance, the syntax is very easy to use. So you are going to define the range minus infinity 0, and then you are going to make a paving of your domain, and you can obtain these pictures. Well, this picture means that you know with certainty in the blue region that your solution is smaller or equal than 0 with certainty. And in the region which is in red, you don't know. So what you can do here is to reduce the threshold and be more accurate in some places as you need. Okay. And to round up, this is what I did, was to compare with a bit higher dimensional model, because I wanted to see if the fact that you produce smaller models has a better performance. And as it turns out, if you take a 3-dimensional system of log table Volterra, then you get around 4,000 constraints, and in the YAML version you get 11,000 constraints, and this has an impact in performance. Okay, so for example, here is around 20 seconds, and for the YAML implementation, you can get around 10 times more. Okay, so to conclude, sum of squares I use sum of squares extension to formulate a reachability problem, and as a future work, we plan to do some more tooling in this GitHub org, and well, also to implement methods for property checking and to extend this to hybrid systems. So thanks for your attention.
Yeah, we got time for one question.
Do you have any reason why y'all would create so many?
Yes. So when I asked Benoit, he told me that this may be because you in sum of squares you can directly formulate in the sum of squares variables, but with YAML you first create the polynomial variables and then constrain them to be sum of squares. So this may be the reason that you get this difference.
So there was a bunch of, looked like the solver was stalling in some of the instances.
Yes.
Were you still able to get like reasonably good solutions? It just wasn't able to merge to the default ones.
Well, yeah. In my case, there is this optimum value called epsilon in the model, and if this epsilon is small, then I have a guarantee on that the solution is good. So in this sense, this is one. I don't know exactly why it is stalled, or if there is another like lower level parameter that I can choose. But this is to say that, for instance, here, yeah, stall something. So when I presented the epsilon here, 0.02, and if I increase the relaxation order, this is smaller.
Thank you myself.
about. Thank you all.